Hello, everyone. Welcome to this introductory webinar on drought prediction and water availability listening sessions and series. My name is Joel Lisenby. I'm the Regional Drought Information Coordinator for the Intermountain West and Southern Plains regions at the National Integrated Drought Information System, or NIDIS, and I'm going to talk more about NIDIS in just a minute. Could we go to the next slide? Before I get started, let's cover some webinar logistics. I think we're all getting pretty used to these by now, but just so everyone's aware, for this webinar, everyone is muted. The webinar is being recorded, and the recording will be available from the NIDIS YouTube channel after the event is over. If you would like to ask a question, you can ask at any time by typing your questions into the question box. In the GoToWebinar platform, the questions box and the chat box are a little different. So use the question box to put your questions in. And the questions will be moderated by Catherine Dom from USGS following the two presentations. And please stick around after the Q&A session. There will be some important information about how to register for the subsequent listening sessions. So that will probably all make a lot more sense at the end. Can we go to the next slide, please? Okay, just a little bit about NIDIS for those of you who may be unfamiliar. NIDIS is an acronym. It stands for the National Integrated Drought Information System. It was first authorized by Congress in 2006 and has been reauthorized in 2014 and 2019. This public law, it prescribes a comprehensive interagency approach for drought monitoring, forecasting, and early warning planning and preparedness to help states and local communities proactively cope with the impact. NIDIS is organized into regional drought early warning systems. I mentioned that at the beginning. I manage the Intermountain West and the Southern Plains DEWs. Those are shown here on this map. Each DEWs is a network of people, or I like to think of it more of a network of networks focusing on, which are focused on monitoring, forecasting, researching, communicating, and planning for drought of various forms. And you can learn more about NIDIS by heading over to drought.gov. You can also get a lot of data and other information about drought in your region. Next slide, please. And now for some introductions. I'm honored to introduce the speakers of today's program, who are going to then introduce a larger project that we'd like some of your input on. I'd like to invite all of the speakers to go ahead and turn on your camera for just a minute and give a wave as I introduce you. First is Brian Clark. Brian is with the US Geological Survey. He works in the Water Availability and Use Science Program. He's the Program Deputy Program Coordinator and Acting Drought Program Manager. He's based in Fayetteville, Arkansas. Sorry, Brian, if I slaughtered that. I'm trying to read what I've written here. Brian is going to provide. Thanks, Brian. Brian's going to provide an overview of the USGS Drought Program. Following Brian, we'll hear from John Hammond. John is a hydrologist with US Geological Survey in the Maryland, Delaware, DC office with the Water Science Center and Drought Program Project Lead. John is going to provide an overview of the USGS Drought Program predictions projects. And then following Brian and John, we'll have a Q&A session, which will be moderated by Catherine. Catherine Dom is a senior scientist with the US Geological Survey, Rocky Mountain Region, and acting Utah Water Science Center Director. Catherine is, well, I mentioned that she's going to moderate the question and answer session. I have that written twice on my introduction. I apologize. I also would like to just quickly thank all of the busybodies who worked behind the scenes to make this meeting happen. They're Marina Stumanich, Adam Lang, and Viva DeHeza from NIDIS. Now we can go ahead and turn your cameras off as we get into the presentations. And Brian, I'll pass it over to you. Take it away.
Awesome. Thank you, Joel. Thanks so much for everybody tuning in today for us to talk about what we have going on in USGS Drought. So I'm going to just try to give a brief overview in a few moments to describe, first of all, why USGS is involved in drought, why we're seeking your input, and we have several of these events spread out over the next few months, as Joel mentioned, why we're seeking your input through those, and a high-level view of where we're headed currently with drought science and USGS. So, John, if you would care to go to the next slide, we're actually going to start at the very, very top, right? So USGS Mission, you can hit that again. There we go. The next slide, we're going to zoom in on that mission just a little bit and highlight a couple of key phrases. So within that, we are essentially bound to monitor, analyze, and predict complex Earth system interactions. And of course, within that, within USGS, complex interactions include climate, forcings, and water resources. So here in the Water Resources Mission area, we have a water availability and use science program, of which I'm a part. I'm the deputy of that program that Joel mentioned. So obviously drought affects water availability, and that makes it a priority for us within water in the USGS. And next slide, thanks, John. So, you know, climate, different climate forcings have long been a part of many of our projects. In many of our water science centers out on the landscape. Several of you may work with our colleagues in those centers on different projects related to drought. But over the last couple of years in particular, we're trying to put a finer point on that with some focused projects. I'm going to look at a couple of those. The first is our National Drought Prediction Project, and that's led by Stacy Archfield. If you happen to register for some of the listening sessions later this summer, you may get a chance to hear more from Stacy on that project in particular and provide some feedback on that. But that project is currently focused on characterization of drought and with regards to streamflow, groundwater, reservoirs. There's probably some other aspects in there as well. And also the relations between drought and extreme events such as wildfire and floods. So again, tune into some of those through the summer and you'll probably hear more from Stacy. The second project that we're looking at is the Regional Drought Prototype Project that's led by John Hammond. And again, you'll hear more about this project in just a few minutes. In that one, we're looking at the potential for data-driven methods to predict drought conditions. And with this one, the regional area we're looking at in the Colorado River Basin. So we're looking at applying these different types of models to predict stream flow and or drought characteristics within the Colorado River Basin. So that brings us to why, you know, we put this whole system of events and really putting a lot of effort into trying to get as much information as we can as terms of needs from just anyone that has different needs, water managers throughout the country. Now, it strikes us as often water managers in particular, water planners may need a straightforward answer to a particular issue. And that's so you can continue with the myriad of other questions that are likely involved in your water planning. So often what you might need or desire, you know, would be, again, something pretty straightforward, simplistic, you know, are we going to have water or are we not? That sort of thing. Well, of course, left to our own devices as scientists sometimes, John, you can hit the next one. Left to our own devices, sometimes that result could be a bit more complicated, right? Sometimes helpful, maybe sometimes not. So we want to really use this information and try to get at the results that are most beneficial. And so with that, you can hit the next slide, John. We can use these listening sessions in the next few months to describe our current roadmap or where we're headed with the drought science program in the USGS and water in particular. That roadmap is currently, there's a few stops on it, and that's with national drought research, which I already mentioned. There's some model development, there's model testing in terms of drought prediction, and an endpoint of a regional prototype and how well that works. Now, what we want to be able to do is use the input over these next few months to inform those different twists and turns we may encounter and better provide tools and science and information for that water planning. Obviously, you know, there's a limit to what can be incorporated, obviously, but we definitely want to be able to hear from folks and inform this type of planning. And next slide, John. We also believe this is a great time as the technology and the data are really coming together and provide better predictions for water resources. And actually, that's going to lead us into this the next talk where John can highlight some of the characterization that he's working on and even some of the where we're at currently with the modeling focus. So I'm going to turn this back over to Joel to transition and look forward to any questions at the end of these talks. So thank you very much.
Thanks, Brian. Thanks for that introduction. We're looking forward to these listening sessions too. I'm now going to pass over to John Hammond to talk to us a little bit more about this specific project. Take it away, John.
Perfect. Thank you very much, Joel. So as Joel just said, my name is John Hammond, and I'm a hydrologist with the U.S. Geological Survey. And today I'm presenting preliminary work on behalf of both the national and regional drought prediction teams. So you might ask, why does this presentation focus on hydrological drought, and in particular, streamflow drought? While there's been a lot of detailed analysis of meteorological and agricultural drought, hydrological drought has generally received less attention. Hydrological drought is a wide-ranging and complex phenomenon that involves streamflow, groundwater, and surface water reservoirs. In this presentation, our initial analyses have focused on streamflow as a way to leverage the USGS network of many thousands of streamflow gauges with long-term continuous data that help us to understand past drought as well as what may be in store in future years. We're seeking your input in the forthcoming listening sessions to adapt and enhance our continuing drought work. The approaches that are shared in this talk are based on preliminary stakeholder involvement, and we're looking for further feedback from you on the impacts, timescales, and drought thresholds that are most relevant. So in the short time that I have with you today, I'll start by defining hydrological drought, and then I'll describe our initial efforts to both characterize and predict that drought by focusing in on streamflow drought. Before we can predict drought, we need to know as much as possible about what we're aiming to predict. This includes answering the questions when, where, and why has drought occurred. I'll then discuss work to predict streamflow drought, where we're attempting to predict the onset, duration, and severity of drought a couple of weeks to a few months in advance. So what is hydrological drought? Hydrological drought is defined as a lack of water in the system, which shows up as unusually low flow in rivers and streams, as well as low levels in groundwater and reservoirs. Streamflow drought can be considered one component of the broader hydrological drought category. While droughts include low flows, a seasonal low flow is not necessarily a drought unless flows are significantly lower than on average. In the diagram at the left, the different components of the hydrologic system are shown, ranging from those at the top that change most quickly, like precipitation, to those at the bottom that change over long time periods, like groundwater. A meteorological drought that starts in precipitation up at the top experiences a slight lag before showing up in soil moisture, and there are longer lags before it's seen in streamflow and groundwater. This representation of drought may appear simple at first, but when you consider the variability in landscape and climate properties across the US, as well as the many ways or the added complexities of the ways that humans store and use water, as shown by the graphics for Fort Collins, Colorado here in the bottom right, the task of both characterizing and predicting drought quickly gets challenging. Hydrological drought is a significant and recurring challenge for water resource management that affects power generation, river navigation, irrigation, municipal and industrial water supplies, among others. Depending on your water use type, your management constraints, and which part of the country you're in, different ways of defining drought may be more useful than others. For example, irrigation water users may specifically be interested in drought that occurs during spring and summer months and relates to a drought threshold that reflects when and where they can pump water from. In comparison, the manager of a fisheries operation may need a way to detect drought any time of the year and based on the flow regime requirements of the species that they manage. In this case, a drought definition that relates to normal flow levels on any given day of the year may be more useful than a threshold based on all days and all years. The two maps at the top of this page highlight existing indicators of streamflow drought using the USGS water dashboard, with streamflow gauges with abnormally low flows in early February shown in the left map, and streamflow gauges that had zero flow for this date in the right map. While both of these indicators may be useful for identifying areas that are in drought, work by the National Drought Prediction Project has been identifying additional metrics and thresholds that help us to characterize and predict streamflow drought onset, duration, and severity for a wide variety of water users and water managers. We'll now move into the characterization component of the talk, which presents initial results from a national scale streamflow drought analysis where we asked, how have streamflow drought duration, severity, and variability differed in space and time in recent history? And second, which climate metrics have driven the variability in streamflow drought, and how are streamflow droughts changing through time? In this analysis, we focused on streamflow drought as an annual phenomenon, but we're also working at the event scale, which can range from days up until multiple years. The figure at the left on this slide shows the thousands of USGS gauges that were used to characterize streamflow drought across the US to address our questions. We selected gauges that only had complete data for 3 periods, 1921, 51, and 1981 until present. We use all gauges for showing the spatial patterns, but we only use data for minimally disturbed gauges, which are those that are shown in color at the left, for interpreting trends and relationships with climate. In order to look at trends and patterns by region, we developed these regional clusters that are shown in color and that are based on similarities in monthly flow. On the next couple of slides, I'll be presenting an example for a site in the Northeast cluster that was in drought in the fall of 2021, and that's shown at the right here. So the figure at the left on this slide shows raw streamflow values from a USGS gauge in the top panel. And then we show streamflow percentiles that were calculated using 2 different approaches in the lower 2 panels. For the static approach, all flows on all days and all years in the period of record are used to calculate one static threshold to define drought. For the variable approach, unique thresholds were calculated for each day of the year using only the values for that day of the year, but from all years of record. We set percentile thresholds of 2, 5, 10, 20, and 30% for drought identification of different severities, where the 10% drought threshold represents a value where 90% of days are not in drought. In this initial analysis, we focus on streamflow metrics at the annual scale. For each gauge, for each year, and for each threshold, we calculated drought duration, which is the total number of days below the drought threshold, as well as drought deficit, which is an estimate of the total amount of missing water, found by summing all of those areas that are shown in orange at the left. For this talk, I'll mostly be focusing on results using the variable threshold method. The figure on this slide shows the spatial extent of drought from 1950 up until present for several regions of the US, where each bar shows the percent of streamflow gauges that were in drought for each year in each region. The red bars specifically highlight years where more than half of the gauges within the region were in drought. For the top example in the Northeast, widespread drought occurrence has been relatively evenly spaced in time. In the middle example for the part of the Midwest, widespread drought occurred primarily early in the record in the 1950s and 60s. And in the bottom example for the Northwest, widespread drought has mainly occurred within the more recent years. These examples highlight that streamflow drought has had varying regional impacts through time across the US. The map on this slide shows variability in drought duration from year to year, with more variable drought in warm colors and less variable drought in cool colors. Higher variability tended to occur in the Southwest, the interior West, the Central Plains, and the Southeast. The areas in cool colors, the blues and some of the greens, do not mean that drought doesn't occur within these sites, rather that on average, when drought does occur, it's of a similar duration and of a similar severity. The map at the top of this slide is repeated from last slide. And now the plot that's been added at the bottom shows the most severe annual drought of the last 40 years for each site, with severity approximated by the total amount of missing flow as compared to an average year of flow at the site. The darkest reds show sites that had the most severe droughts over the 40-year period. Over this period, the interior West and California generally displayed the most severe streamflow drought, as well as some areas of the Central Plains. Low water levels during the drought of 2011 and 2012 in eastern Iowa led water to heat faster and to reach higher than normal temperatures, which then spurred algal growth and subsequent oxygen depletion. Numerous outbreaks of toxic algae were reported, and this emphasizes the effects that drought can have on water quality as well as aquatic species. Our second question asked, what climate metrics explain variability in streamflow drought, and how are droughts changing through time? The map at the left shows trends in drought duration across the country for 1950 to 2020, while the map at the right shows these trends for the shorter period of 1981 to 2020. The sites where drought has become shorter and less severe are in blue, while places that it's become longer and more severe are in red. For the period at the left, 1951 to 2020, decreases in drought duration and deficit were evident in the Northeast, but we also did observe increases in drought in the southeast and in the northwest. For the period at the right, 1981 until 2020, we saw increasing drought duration and deficit expand in the southwest and the south central US. Our analysis reports that in the southwest, where drought deficit and duration have increased, these increases have been about sixfold. Annual aridity showed the strongest relationships with streamflow drought at the annual scale, and these relationships between aridity and streamflow drought were very similar for using climate from the present year as well as using climate from the prior year. Temperature generally showed weaker relationships with drought, except for in certain areas of the western US. While the analyses that were shown in the prior slides focused on drought at the annual scale, the effects of drought can linger from year to year, compounding and resulting in lower water availability in groundwater and reservoirs. In the top figure for a site in New Mexico, we show the cumulative missing water in recent years, with increasing amounts of missing water paralleling the decreasing trend in reservoir storage, as shown by the time series from Elephant Butte Reservoir at the bottom of this page. The boxes in red and blue over at the right show the reservoir extent observed from space for 2 points that were added to the series at the left. And this helps to highlight the effects of the multi-year decline. As we continue to characterize drought, USGS projects will focus on the propagation of drought from precipitation and snowmelt into soil moisture, from there into streamflow, groundwater, and reservoirs. And we'll also work to assess how hydrological drought develops in mostly natural areas as compared to highly human modified areas. This slide marks the transition from initial efforts to characterize streamflow drought to other efforts to predict it. On the national project, scientists are working to determine when and where drought onset is easier to accurately predict, as well as to identify the data sets that are most important to predicting drought in different regions. The figure at the upper right shows the results of initial modeling, where areas in cool colors display more accurate prediction of drought onset, and areas in warm colors show lower initial accuracy. On the regional drought project, scientists are focused on machine learning methods for early warning prediction of drought. We use the term early warning to describe our efforts to predict drought a week to a few months in advance. Early warning is a unique focus and goal of the regional project, where scientists are trying many methods and many data sets to identify potential approaches that work in one region, could be transferred to another region, and eventually could be applied at national scale. The regional drought project scientists are trying to answer the following questions. What methods give us the best estimates of drought onset, severity, and duration? How early can we accurately predict these drought metrics in different areas? And can we predict drought in heavily human modified areas of the basin, as well as in the more natural areas? One quick note on the next slide, we have an animation that has some flashing red and white areas. So it's a small area of the slide, but please be aware if you have any photosensitivity. So I'll now provide a little bit more information on initial work by the regional drought team. In the figure at the left, we show our study area of the Colorado River Basin, with the upper basin in light orange, the lower basin in dark orange, and streamflow gauges that had long-term complete data as black points. In the animation in the center, watersheds that were in drought for any given time show up as red in this weekly animation from 1981 up until 2020. The USGS has been monitoring streamflow for a long time, and because of this, we have a lot of high-quality data that's available within the basin. Approximately 7 million observations of drought or no drought in daily streamflow are available over the period that we're modeling. This large data set availability offers machine learning methods the ability to excel. In order to predict drought in the watersheds across the basin, we're using daily time series of meteorology, as well as satellite estimates of snow-covered area, irrigated area, and reservoir, lake, and pond storage. In addition to those time-varying inputs, we're also using static estimates of soil and bedrock characteristics, land cover, topography, and geology. So this project is very much a work in progress, but we already have some strong preliminary models for the natural areas. Initial work on the regional drought project is focused on exploring the variability in our drought target data sets, which the models are being used to predict. Project scientists have been building workflows both for cloud and high power computing model development. We've been implementing initial random forest models and neural network models and using approaches that work in streams that flow all year, as well as those that go completely dry for part of the year. We're starting to develop and refine model evaluation techniques and selecting thresholds of interest to stakeholders. And finally, we're preparing our workflows for adaptation to other regions, to other input variables, and with the eventual goal of operational model implementation. We've identified our biggest difficulty moving forward will likely be predicting drought in the heavily human modified areas that contain many diversions, wells, reservoirs, and other types of both flow and landscape modification. So while we think we've made a strong start at characterizing and predicting drought, our work is only beginning. Ongoing work by USGS scientists address the many components of the hydrologic drought, including snow, soil moisture, stream flow, groundwater, and reservoir drought, as well as the relationships between wildfire and drought, ecosystems and drought, floods and drought, and ultimately how drought impacts and interacts with our complex managed systems. I'd like to thank you very much for your attention, and we're looking forward to your feedback on the impacts, the timescales, and drought thresholds that are most relevant to you. Thank you.
Thank you, John. Thanks for all of that background. Now I'm going to invite Catherine to moderate the questions for our two presenters.
All right, thank you, Joel. And as a reminder, following this short question and answer session, we will walk through the information on how to register for the upcoming end user listening session webinars, where we're looking for your input and feedback. So just to start us off, and thank you for those who have already entered questions, feel free to continue entering those in the chat box. This is a question probably for John, but John or Brian, how do you separate drought from what is becoming the norm? The problem is that drought ends and this new norm won't. How do we encourage the public to understand the difference and modify our practices to live within this new norm? John, do you want to take that question?
Yeah, I'm happy to give an initial response. So that's a great point by the listener that, drought is becoming the new norm in certain areas of the country. And, within our initial characterization efforts at the national scale, one of the areas that is really highlighted is, parts of the Southeast and the Southwest where, drought has really increased over the past, 50 or 40 years. And, that's really critical for us to have identified. I think it's, part of the common knowledge around drought, but it's something that we need to know in order to be able to incorporate that into our modeling approaches. Because if you developed a model without that model also being aware that drought has become more frequent in time, it might, make incorrect predictions because it wasn't informed, that basically the predictors' relationships have changed. So we're building models that, the scientific term for this is non-stationarity. We're building models that account for that non-stationarity within the data so that the predictions that we produce are more accurate. But, the listener's other point of that question, how do we communicate this information to the public? I think that's an ongoing, a great question and something where, our work is very much ongoing in terms of, how do we communicate that? And I think during the listening sessions, that'll be a great opportunity for us to kind of have that conversation go back and forth so that we can come up with the best language and best materials to communicate that.
Great, thank you, John. The next question we have is, and it was posed early on, but it'd be great if you or Brian would speak to it, John. It's related to whether or not the webinar and the listening sessions that are scheduled are limited to hydrologic drought for those who are interested in forecasting of ecological drought. And we do have an end user listening session specifically related to water availability for ecosystems that'll come up in September. But Brian and John, either one of you, would you like to speak to how this series also is related to ecological drought information?
Sure, Catherine, I can mention that real quickly, or probably any one of us can. But as far as the ecological aspects, there's actually is a listening session coming up later this summer. So, and I think you said you'd be providing some of the links and some of the instructions on how to go about joining that later. That was correct, right?
Yeah, I think Joel will cover that in the next session. But continue, Brian. Go ahead.
No, John, did you have anything else you wanted to cover on that one?
Yeah, I can just say, in our day-to-day work at the USGS, we're talking amongst, say, the water mission area as well as the ecosystem mission area. And so, we're having those conversations. Just yesterday, I was doing a dry run of this presentation and was contacted by someone who's really focused on eco flows and ecosystem water use. And so we were talking about kind of coordinating our efforts so that, what we do specifically to predict drought uses metrics that are able to be taken and used to relate to observations of kind of ecological processes and ecological needs.
Thanks, Brian and John. And a somewhat related question to that, this is probably for you, John. Will this project or subsequent work look at trends or variability in stream temperature?
That's an excellent question. I think currently, the scope of the regional and national drought projects is more focused on the water quantity, but we definitely know that the quality of that water, whether it's temperature, whether it's dissolved oxygen or salinity, et cetera, is very much related to the water quantity as well. So I think as we get further along the pipeline with these projects, as we get beyond some of our initial results and start to make more of those connections, I think we will be getting there as well.
Great, thank you, John. So the next question that we have is, what are the limitations of the current state-of-the-art models, especially those developed by the USGS, but you're welcome to speak to others, in predicting streamflow droughts for an extended period into the future, say 1 to 2 years?
Yeah, I can give an initial answer to this, and then Brian, Catherine, if anybody else wants to join in as well. Some of our biggest uncertainties within the models would be, the representation of the many ways that humans store and use water. So that's one big uncertainty. And then the other big uncertainty would be, the further that we get out, from present day in terms of, how much precipitation we're going to have, how much of it's going to evaporate, how warm is it going to be. The further and further that we go out, the less certain that those predictions become. So it's really important that we use ensemble predictions that kind of cover the range of what the likely future precipitation and temperature could be. But I did identify those two as being kind of our primary sources of uncertainty within the models.
Thanks, John. Brian, did you have anything you wanted to add to that one?
No, I think that's good. Thanks, John.
And I appreciate the question, and it would definitely be worth something diving into within the listening sessions, is to hear a bit more about uncertainty. That's actually one of the questions that we're posing to those that are really end users of this science, as to what the given accuracies and uncertainties that you're challenged with and what your needs are, really focus on, so we can better understand how that impacts what the USGS is producing. And so, somewhat related to at least the methodology you're using, there's a specific question here, John. Given that you're using undistributed stream flow points for this work, roughly what stream order or HUCs are the streams you have analyzed?
Yeah, that's a great question. There's a really large range in the size of watersheds that are being used as kind of the input time series to the models. I think some of the smallest watersheds are even smaller than 5 square miles in area. And then we do have, once you get further down on the main stem of the Colorado River or some of its tributaries, we do have, gauges that are hundreds of thousands of square miles. And so, different types of modeling approaches will probably work better to generate the predictions in those different sizes of watersheds. So some of those really small watersheds tend to be in the headwaters, and they're mostly natural. So kind of our first approach to modeling is developing that model for ungauged areas. And so we would probably start with that model for those small headwater areas. But for those really large watersheds that are downstream and have a lot of kind of added human flow modification, those are areas where we're adding another tier into our modeling where, where we can, we'll assimilate data in. So look at the most recent reservoir storage, look at the most recent stream flow from a gauge that's upstream of that site. And that approach will hopefully lead to more accurate predictions for those types of gauges with those large drainage areas.
Thanks, John. The next question is related to just cross-coordination between groups. So there's a question as to whether the USGS is working with the National Weather Service River Forecast Centers and the National Water Center in their modeling efforts. That can go to either Brian or John.
I think the short answer would be yes, but John, if you have some information on just the interaction or maybe just the data sharing, the way the river forecast centers might, or the way we utilize their information as well.
Sure, yeah. So I'll just, first start off, especially the regional drought early warning project, that's very new to this year. So that project only started back in October. So we've been really focused on, getting some initial results that are then, more useful when we make those connections with the other federal partners, so that we can kind of say, here's what we've got, here's what we're doing, and how might what we're doing or what you're doing lead to kind of co-benefits. So we haven't explicitly made those connections to the river forecast centers just yet, but it's definitely within the plan. And then I'll just mention some other work. We know that both NOAA and USGS with their kind of continental scale hydrologic models, they're looking at kind of examining where the models are getting flow predictions right and where they're getting them wrong. So there is a lot of work there between the agencies.
Yeah, thanks for speaking to that. I think that within the federal family of science organizations, it's always hard to discern how folks are working together, and there's definitely relationships across the landscape. And that's, part of this effort is looking to form and continue to strengthen those collaborations. I appreciate Brian, both you and John weighing in on that question. We have a question that I think gets back to this ecological drought aspect and maybe impacts of the terrestrial system or the upland areas. The question states, I know all the reference sites are relatively undisturbed, but do you expect forest regeneration in some of these young forests that will actually impact some of your drought severity metrics? And if so, is there any way to account for this?
Yeah, that's an excellent question. So in one of my slides, I talked about the various types of input data sets that we're using, some of them being time variable, as well as some of them just being static. And for now, what I said was, we're starting off with static estimates of land cover, which could include the percent open water, the percent within forest cover, percent impervious area, et cetera. And we're just doing that because that's something we already had generated for all of the modeling units that we're using. But once we have our initial models generated, we do have access to that time varying estimate of forest cover that's observed from satellites, and we have that basically at an annual scale. So we'll include that as a predictor in order to see when we do include that time varying land cover, if that is chosen as an important variable in the model. In terms of kind of representing the process change there, for there potentially being increased transpiration. You could have changes to the snowpack when you have that higher forest cover. So yeah, an excellent question. I don't think we're quite at the point of being able to answer it fully just yet.
Thanks, John. And somewhat related is this question as to, is there any accounting for changes in runoff efficiency? I know there's been lots of work that's been done, particularly in the Colorado River Basin, on snow to flow type information on what type of runoff efficiency has occurred. And I know you mentioned that, but do you want to speak a little bit to looking at runoff efficiency as part of the drought prediction project?
Yeah, another great question. And so we know that one of the slides I showed that from year to year, the effects of drought can compound. So if you have drought in year 1 and you have that drought continue into years 2, 3, 4, you're really depleting, how much water you have stored within groundwater, how much water was within the soils, et cetera, so that when you do get some sort of new input, whether that's precipitation or whether it's snowmelt, you kind of have to exceed that deficit that you've already developed within the soil moisture and into the groundwater before you really start generating the same amount of flow as you did in the past. And one thing I'll mention here is, this is part of the reason that we have these two different projects currently. There's the National Drought Prediction Project and the Regional Drought Prediction Project. And the Regional Project is really focused on, those methods of prediction. What can we do? What are the best data sets? What are the best methods for getting us the best accuracy of early warning prediction? But the National Project does have a little bit more of a focus on delving into the processes that kind of control that propagation of drought. So say there was a drought within the snowpack, so you had low snow conditions for 1 year or for multiple years in a row. That national project is really focusing in on how that affects runoff efficiency, how that affects multi-year runoff generation, and ultimately water availability. So it's definitely something that's on our radar, something that we're working on, and something that the Regional Drought Project will benefit from the results of the national project.
Thanks, John. So we have a couple of questions about resources that are available that are non-USGS resources and utilizing other federal, state, and local resources. Specifically, there's one question regarding, at the current time, are you using any non-USGS gauging stations in your data set? For example, in Colorado, the Colorado Division of Water Resources has a very large long-term stream gauge network that would enhance the larger stream gauge network. Can you speak to the current practices and then what's planned for the project with regard to stream gauges that are outside the USGS network?
Sure. Yeah. So, that's completely correct. Currently we're just using the many USGS gauges that we have in the network as kind of a low-hanging fruit approach to get our initial models built. And even just with the USGS, streamflow gauges, we have those 7 million data points that are scattered all across the of the Colorado River Basin and some of the adjoining areas. But we definitely do want to include as much data as possible. So we are planning to pull in data from other agencies, whether those are national or state agencies, where they have streamflow data. And then something I will mention, in addition to streamflow data, we are already pulling in time series of reservoir storage and reservoir elevation. That's from the U.S. Bureau of Reclamation, as well as the Army Corps of Engineers, and a couple of other sources. So yeah, the more data, the better, especially with these data-driven methods, these random forest and neural network models. The more data, the better, and that will hopefully, improve our predictability, not only, across the entire basin, but, if you have a gauge in an area that's not currently gauged by the USGS, but there's other gauging there, including that gauging would, likely improve our ability to predict in that area.
Thanks, John. And related to more data, we have a question on, has there been testing yet on sensitivity to inputs related to streamflow, particularly soil moisture or snowpack? And where do you think better observational data should be focused to improve predictability beyond streamflow data?
Yeah, we're very much in the midst of doing that testing right now. So I mentioned that, for the regional project, those initial models have been built, and basically what the project scientists are doing now is they're analyzing, how much predictive capacity do we get from one variable as compared to another, and which variables can we actually remove from the model because they provide us, information that's maybe redundant with something that's already included in the model. And kind of reducing the number of variables that are used for prediction is something that we're really interested in, especially when we think about scaling up to, say, a national extent, in terms of like the computational efficiency. If we want to be running this eventually, not right now, but eventually, if we want to be running this every day and for, the entire country, having a really succinct list of input variables would be beneficial. I do think, especially, if I'm thinking about the Colorado River Basin, including both better information on the snowpack distribution and the snow water distribution, as well as, how much water content is within the soils. Those would both be really good data sets for us to include. And we do have, I'd say we have more data to work with on the spatial distribution of snow than we do on the spatial distribution of soil moisture. And there we mostly have to rely on, various modeled products. But if there are products that people are seeing be developed and be released, we're definitely interested in hearing about them.
Thank you, John. And we have a couple questions, particularly about looking at areas, either ungauged areas or areas outside of the national scale effort. So particularly island communities or Alaska. I'm curious if you'd like to speak a little bit just to the breadth of application and the transferability of this type of methodology to locations that weren't in your initial results slides that you presented today, or maybe part of the longer term plans.
Sure, yeah, I'll give an initial answer to this, and Brian, I think you'll probably have a lot of great information on what's happening at the drought program level. But I think, because there's so much variability in climate drivers and landscape alteration, et cetera, just within the lower 48, the plan was to at least develop those methods within that area. And, all of the workflows that we're developing are, they're in GitLab, they're in GitHub, they're set up in a way that they can be easily transferable to other areas just as soon as we basically download the data for those areas. So I'd say, the workflows exist or will exist in order to do that. But just, I guess it's just not currently within the scope of the projects that I've been working on.
Catherine, can you run that by me one more time? I was listening to John. What was the program part of the question?
Yeah, the program, future program direction for extending beyond the current focus of John's preliminary, John and Stacy and the team's preliminary work to be look at island communities, Alaska, areas outside of the continental United States.
Oh yeah, right. Well, and drought's one program, like John had mentioned. Right now we're focused regionally and want to carry those methods forward to the national scope. But we also have work in like our integrated water availability assessments and integrated water prediction, where we're looking at not just drought prediction there, but just overall water availability prediction. So, stream flow and groundwater inputs, water quality aspects of that. So there's multiple programs in water resources that we're looking at beyond drought that would probably venture into those data sets and set up the framework for those types of models initially, so that then we could hopefully expand with all of these different kind of metrics that affect water availability, including drought, into those OCONUS areas, if you will.
Thanks, Brian. Well, for our last question for the question and answer session, just before we start to transition into hearing really from you all that are on the call about how you can participate in giving feedback. The last question that we're going to be able to get to today, and we will follow up. There have been a lot of really excellent questions in the question box, some very specific, some I know that we just touched on and some we weren't able to get to, but we will follow up on those. The last question, just as a lead into the presentation, the end of the presentation that Joel will cover about participating in the listening sessions is, will specific drought or water availability questions or topics for which your team is most interested in soliciting stakeholder feedback, what will those types of questions and topics be for the group? And I know Joel is going to go over the plan for those sessions in a bit of detail, but since John and Brian are both on the line, maybe hearing from you for things that you're excited to hear through the listening sessions, from the folks that will be participating. If you have any specific topics or interests you're interested in hearing about, feel free to mention those. And let's start, Brian, how about we start with you and then we'll go to John second.
Yeah, well, kind of as I even outlined in the first few slides there before John's talk, I'm really interested in, what that endpoint need is, so that we're not perhaps overcomplicating the science that's produced, and how we can kind of get at the needs and the usefulness of what we might be able to produce. So using these listening sessions to really inform that, I'm obviously excited about that, and how everyone is using current predictions or the needs of what those current predictions would be, and the time frames and the spatial and temporal aspects of it. So there's a lot there to unpack, but yeah, just really want to get at those kind of questions, those kind of discussions, and really looking forward to that over the next few months.
Perfect. Yeah, and I'll just add on to that. I showed a couple of slides where, our current methods in order to define and to characterize hydrological drought, whether it's in stream flow, reservoirs, or groundwater, we're using a couple of different approaches, approaches that rely on one static threshold or one where we kind of account for the seasonality within the year, that variable approach. And we're also currently using, those multiple levels of different thresholds, for the lowest flows, something like a 2% threshold, up to, kind of mid-range flows at 30%. And so I think some of the feedback I'm really interested in, some of the conversations I'm interested in having, revolve around, what is the definition of drought, or like at what point does drought start to impact the various types of water users and water managers who will be attending the listening sessions. So that would really help us to kind of hone in and to develop something that will be of use to a lot of people.
Great, thank you both. And I'll add in for my personal opinion here that working out on the landscape in a specific geographic area, I personally am really looking forward to having some discussions with folks about challenges and unique aspects of everyone's different landscapes. And during the listening sessions, we'll be able to break out not just into discussions about larger national questions, but also local areas. So with that, I really want to thank Brian and John for taking the time to answer a whole number of different questions. I did mention we weren't able to get to all of the questions that were asked. There are a lot of excellent questions that we will make sure to follow up on. So again, thank you all for taking the time to participate and submit questions. At this time, I'm going to transfer the discussion back to Joel so he can walk through how to register for the upcoming end user listening sessions.
Thank you, Catherine. John, can you go to the next slide, please? So as we've alluded to throughout this meeting so far, today's meeting really just kicked off this project. It's sort of a pitch project of a pitch meeting of what's happening. And we're going to be holding a series of listening sessions over the course of this year, where we want to hear from you about what's important. The dates for those have already been scheduled, and I'm showing them here on the calendar. It's March 3rd, where we'll be focusing on stream flow drought predictions. May 5th is about groundwater drought. July 14th is about water use information. September 8th is about water availability predictions for ecosystems. And October 20th will be a final shorter meeting. It's just a wrap up of this is the things that we've learned throughout the year. Each listening session will be virtual. We're going to be hosting it using Microsoft Teams. They'll all begin at 1 p.m. Eastern time, and they'll probably last about 2.5 hours each one. Go ahead to the next slide, please. So what are we listening for here? We've talked a little bit about that, and Catherine just summarized some of the points that both Brian and John would like to hear. These are a few of the questions that we know that we are going to be listening for as we go through these listening sessions. How does hydrological drought affect you and your job? How does it cause pain and difficulty in the things that you're trying to accomplish? What tools and information do you currently use to anticipate changes related to hydrologic drought conditions? And of the information that you have, what's missing? What would a good hydrologic drought forecast look like for you? What are the timescales that are important? What are the formats that are important? What tools would you like? Any other special considerations that the project team should be listening for, and anything else really, any suggestions you may have, etc. Next slide, please. So how to join? Marina has just put into the chat box a link to a Google form. This Google form will give you an opportunity to register for these individual listening sessions. You can join as many or as a few as you are interested in or have time to. The same form was leaked in a previous email, and if you've already clicked on that link and fill out the form, then you're good to go. And also watch for a follow-up email, which will have links to this recording of today's webinar, and also a link to the form that if you don't get a chance to look at it now, you can do it at any point in the future. And that's it. Can you go to the next final slide? That concludes today's meeting. I would like to thank Brian, John, and Catherine for kicking off this project with us and inviting all of us to be part of this project. Thank you to all of you for joining today. We really look forward to hearing from you later this year, and please stay well.